Good morning, grade 11s. In this video lesson, I'd like to discuss the rest of the questions in exercise 2 on page 22 and 23 in your textbook. I just need to make sure that we get all the concepts there. So it's exercise 2 on page 22 and 23, and we stopped in class at number 4, 5. So I'll start here at number 5. We've got a crate at rest on a slope, and they want us to draw the force diagram as well as the free body diagram for the situation there. I'm going to look at the free body diagram only. So we've got a slope that is at an angle of 15 degrees, and the object is resting on the slope. So we will reduce the object to a dot. There will always be a force of gravity, and the force of gravity will be perpendicular to the horizontal, that is that level there. There will always be a normal force if the object is resting on a plane or on a surface, and this normal force will be equal to the perpendicular component of the weight. So it is this component. I don't want to draw it in here, but it's this component here. And there, the next force would be the frictional force. Now, this object will tend, it's at rest, but it will tend to want to move down the incline. So the frictional force will be in this direction here, and it will be a static friction. The magnitude of the static friction would be equal to the magnitude of the component of the weight parallel to the incline. So that is my free body diagram. I'm going to redraw the free body diagram using the components of weight so that you can see the difference. So here we go. If I use the components of weight, then it would be the component of the weight perpendicular to the surface, and the normal will keep that in equilibrium. So the normal would be the force of the surface on the object. The friction would be up the incline, and it's still static friction. And the parallel component of the weight will have the same magnitude as the friction. That brings us to the end of number 5. Number 6. Number 6. As the crate sliding down a slope against friction at constant acceleration. If the acceleration is non-zero, it means that there is a net force down the incline that is also non-zero. Now this incline lies towards this direction, slopes like that, and the angle is 20 degrees. Now, take note, there is no applied force on the object. It's because of the slope and the parallel component of the weight down the slope that it will accelerate down the slope. So for the first example that I want to draw is the FG1. The normal force will be perpendicular to the slope, and there would be a friction. The friction will be much smaller than the parallel component of the weight, because those two forces are no longer in equilibrium when your net force is non-zero. This, because the object is moving, is a kinetic friction. To represent the same situation with the gravitational force's components, I'm going to do this, 20. Now, you've got the perpendicular component of weight, Fg perpendicular, and you've got the parallel component of weight, Fg parallel. You've got the normal force opposing the perpendicular component of the weight, and the friction, but in this case, the friction is smaller than the parallel component of the weight. Good. So that brings us to the end of number 7. Next is number 6. Next is number 7. I'm going to, if you need to copy all this still, you need to pause the video to do that, because I'm going to clean the screen now so that we can go to number 7. Number 7. Number 7, you've got a strange situation. You've got a 3 kilogram object resting on a flat surface that is connected by a string running over a pulley to a 5 kilogram object there. So here you have the 3 kg object, and here you have the 5 kg object. Now, to identify the forces on the 3 kilogram object, there will always be a weight that goes straight down. There will be a normal force, and this normal force would be this normal force would be equal in magnitude to the gravitational force, because they are in equilibrium. There would be a tension in the string pulling to the right, and they said it's a rough surface, so there will be friction. Now, it's joined by a string passing over. The system accelerates clockwise. That means that this friction is a kinetic friction, and it would be less than the tension. So I'll make that arrow shorter. So this whole thing accelerates to the right, or the 3 kilogram blocks accelerating to the right. The 5 kilogram block will be moving downwards. Now, a pulley has the amazing property of changing the direction of pull. But because the same string is joined to the 3 kilogram object, the tension that runs through that string is the same everywhere in the string. It's just now the tension is up the string from the 5 kilogram object. Because the object is accelerating, the system is accelerating, this tension is less than the gravitational force, and it has the same size as the tension in the string where it is linked or joined to the 3 kilogram object. So here we have two objects joined, and each object has its own free body diagram. I'm moving on to number 8. Number 8 has two boxes that are joined or next to each other on a surface. You've got A and you've got B. Now, it doesn't look like that, but it's the same type of situation as when A and B are linked by strings. I promise you, it's the same. You just don't have tension because you don't have the string. But A will still push against B, and B will push against A. If I have a force applied here, A will push on B, so that is the force of A, but B will push back on A with the same magnitude force. Those two forces will be exactly the same. In number 8, they said it's frictionless. This surface is frictionless. And the whole thing accelerates to the right. We are going to draw a free body diagram for each of the objects separately. So here we have A. There is a force applied to A. Force is applied to A. And B pushes back against A. Now, because the objects are accelerating to the right, the force to the left is smaller or weaker. So this is the force of B on A. Those two forces are not the only two forces. There is a gravity pulling on A, and there would be a normal force pushing up on A. Those two forces are in equilibrium, so the arrows you can draw more or less the same length. For object B, there is no applied force on object B. The only force in the horizontal direction for object for object B is the force of A on B. And I think I'm drawing it too long here. I need to make it a little bit shorter, because that force, the force of A on B, is the same as the force of B on A. But the direction is opposite, so I give the one a negative sign. Then the other forces acting on B would be the gravity and the normal force, and those two forces are in equilibrium. There we have the two situations for A and B. You need to pause the video to finish your copying. Do so, because I want to go on to number 9. Number 9, you have a crate pulled uphill against friction. here is an applied force on the crate. Let's draw the force diagram. Here's the crate, angle making 20 degrees, and there is a force applied up against friction. So there is friction there. I guess the guy is moving the crate up, so it's a kinetic friction. There is a gravitational force. Oops, this arrow is a bit skew. There is a gravitational force acting on the crate, and there is a normal force that will be smaller than the gravitational force because of it being equal to the component of the gravitational force. Sorry. So the free body diagram for this situation is the applied force, the kinetic friction, the normal force, and the gravitational force. Just to fill you in, the normal force will be equal to the component of gravity perpendicular to the surface. And there's also a component of gravity parallel to the surface. So you could fill that in if G parallel. But if you draw that as part of your force diagram, you don't put Fg in. Last one in this exercise is number 10. Number 10, an object is accelerated upwards by a rope in a vacuum. So in a vacuum means that there is no friction or air resistance at all. So this 10 kg object is attached to something that accelerates it up, and that rope will have tension. Because it's accelerating upwards, the acceleration is upwards. The net force is upwards, so tension must be greater than Fg. Fg must be smaller than the tension in this case. Right, I hope you found these answers useful and that you're growing in your understanding of vectors and forces. Thank you for watching.